Welcome to Math 2318, section 2.8. In this section, we are looking at subspaces. What is this thing called a subspace? So, H is a subspace of a particular thing called a vector space if three things are true. One, H is a subset of the space. Okay, so symbolically, H is a subset of the space. A space can be a subset of itself. Now, 2 and 3 are the most important properties, and that is if I take two elements in this set and if I combine them during using the addition operation, if that sum is still in the space, we say that the operation is closed under addition. So that has to be true for all U and V in H, that all combinations are still in the space. And the third thing, if I have a real number, then if I do scalar multiplication by positive numbers, negative numbers, all possible values of C, it's still in the space, then it is closed under scalar multiplication. So to be a subspace, all of those things must be true. And as a consequence of that, what that tells me is that to be a subspace, 0 must be an element of the subspace. So, if I look at any subspace of Rn, it must contain the origin. If you have some set and the origin is not in there, then it cannot be a subspace. Alright, so looking at the homework. So, in question 1, we are given things in quadrant 1 here. That includes the positive axes. It includes the origin. Question is that a subspace or not? So let's see. Here's my subspace. Here's H. Is it a subspace? Well, let's see. 0's in there. Yes. If I take two vectors and I add them together, is that still in there? Yes. If I multiply by any positive scalar or even 0, that will still be in quadrant 1. But the problem is if I multiply by a negative number, so minus C times vector U, it's not in. Remember, here was supposed to be our subspace H. It's not in there. So it's not closed under scalar multiplication. Therefore, it is not a subspace. In question 2, we try to fix that problem. So let's see. We have the axes. We have quadrant 1 and quadrant 3. Is this a subspace? Well, let's take a look. Alright, so yes, the origin is there. If I do any kind of scalar multiplication, positive or negative, that's still going to be in there. And the question is, well, what about, is it closed under the addition operation? And is it always true? Not just if I take 2 in each side, but is it always true no matter the combination? Well, let's see. Let's say I have vector U points to 2, 2, or 2i plus 2j. Vector V points to minus 1, minus 4, so minus 1i minus 4j. And if I add these two vectors together, my U and V, I get I minus 2j, which points to 1 minus 2. Well, here was H. H was things in quadrants 1 and 3. I now get something that lives in quadrant 4. So this is not closed under the addition operation. All right, so here in this problem we have V1 and V2, and I want to see if W is in the subspace spanned by these two vectors. So is it possible to find C1V1 plus C2V2 equal to W? So I simply put in my columns, put in W, and now do row operations. So I'm using this 1 to make 2 zeros. All right, at this point, I can divide this row by 4. And so now I have this 1 to make some zeros. But when I do that, I see I get 0, 0, minus 1. So there's no solution. So what that tells me is there is no constants where this is true. So W is not in the subspace spanned by V1 and V2. All right, in this case, we have a U in R4. Is it possible to find C1, C2, C3 where the sum is going to be equal to U? So again, we got V1, V2, V3, and U. I'm looking to see if I can solve this for my constants. All right, so use the 1 to make 2 zeros. I'm looking here at row 4. I can divide this by minus 5, giving me a 1. Use it to make 2 zeros. All right, once I do that, I'm looking here at row 4. Divide that by 3. All right, and that gives me this one. And I'm noticing these are the same, row 3 and row 4, so I can eliminate it. And once I do that, I can use the 1 to make some zeros. And I find, yes, there is a C1. C1 is minus 15. C2 is 5. C3 is minus 2. So yes, there are constants, which when I multiply them by V1, V2, V3, it will give me U. All right, we want to determine if U is in the null space of A, where A has V1, V2, V3 as columns. What is this null space? Well, the null space is the collection of vectors where A times that vector is 0. Okay, so if U is going to be in my null space, then A times U has got to be the 0 vector. And the null space is a subspace of the space. All right, so let's see. Is it true? A times U, so here's A, here's U. Perform the matrix multiplication. And yes, I do get 0, so yes, U is in the null space of A. All right. In question 6, we have matrix A here. Now, matrix A is 2 by 4. And they tell us that matrix A is going to work from RP to RQ. All right, seems straightforward enough. Well, let's see. If it operates on something in RP, Well, A is 2 by 4. And to operate on something on X, the number of columns of A has got to match the number of rows of X. So that means that has to be a 4 by 1. So the null space of A is going to be a subspace of R4, so P is 4. Well, what does the image look like? Well, 2 by 4 multiplied by a 4 by 1 gives me a 2 by 1. So the image, or the column space of A, has got to be a subspace of R2. All right. We want to find out if these two vectors form a basis for R2. Well, what is this basis thing? Well, the basis thing is a collection of vectors. They have to be linearly independent. And any vector in the space can be written as a combination of those basis vectors. In R2, you have I and J, 1, 0, 0, 1, which we call E1 and E2. So any vector V in R2 is a combination of those two basis vectors. R3, you have I, J, and K as typical basis vectors. So, well, what about these two vectors? Well, let's see. What's the determinant? The determinant is minus 72 minus a minus 128. The precise number is not important. What is important is the determinant's not 0. So A is invertible and its columns do form a basis. In question 8, same question. Can these two vectors form a basis for R2? You might be thinking, well, doesn't R2 already have a basis, E1 and E2? Yes, but a space can have different bases. So let's see. Here's A. I calculate the determinant again, so that's 30 minus 30. The determinant is 0, so A is not invertible. So the columns of matrix A do not form a basis for R2.